Evaluating limits at infinity is the idea of evaluating as x is approaching positive infinity and approaching negative infinity. And visually what that's doing is, in terms of a graph, whatever our graph may look like, if we're looking as x approaches infinity, that's this idea of going off to the right-hand side. That's where x is approaching positive infinity, and where x is approaching negative infinity is going off to this left-hand side. As x goes to negative infinity. And so what we're looking at is what's happening out as we go to the right and as we go to the left. And those sections of our graph, it's called the end behavior of our graph. Is that what is it doing in the long run of everything? As it just goes off, if it's going off to infinity or if it's going off to a horizontal asymptote, what value is that? So that's what we're doing here with limits of infinity. Is if we're going to talk about these, it's the idea of talking about the end behavior of these graphs. Another term used is long run behavior. So some of this may and hopefully does sound a little familiar from pre-calculus, and we'll talk about it in that way. But also I'll talk through this idea of what does it mean to plug in infinity? What can we do and what can't we do when we do that? So, okay, so for each of these, we're going to evaluate the limit as x goes to positive infinity. So let's talk about this first one. As x goes to positive infinity for negative 5x cubed, and as we go to negative infinity for negative 5x cubed. So let's see what happens when we do just plug infinity in. So it would look like a negative 5 times positive infinity cubed. Now something that happens with these, if you think of infinity as this vastly large number, this 5 and 3 really doesn't have much influence. Is that if we're at infinity and we cube it, well, it's just getting even more infinite, so it's really just still infinity. Multiplying it by 5, still infinity. Something I do care about is that negative out front. The fact that we have a negative value times infinity. So the 5 and 3 kind of get absorbed by infinity, but the negative does not. So we just go, this would be negative infinity. And if we do the same thing with the negative 5 times negative infinity cubed, similar ideas, just now that we're at a very small number, a very negative number, and if we cube it, that actually gets even more negative. So when we cube, we still have a negative out. So this is kind of like a negative, let's even keep the 5 in, negative 5 times negative infinity. And we're going to have the same property of negative times a negative makes a positive. So that's going to be a positive infinity. So that's kind of, I'm almost hesitant to call it the algebraic way because it's a little different with infinity, but it is kind of this idea of plugging in infinity and simplifying. Now the topics in pre-calculus, we talk about long-run behavior. So this is our cubic function, and a cubic function typically looks like this, but with the negative out front, it reflects it. So this is a cubic function that looks like this on our graph. So as x approaches positive infinity, as we go off to the right-hand side, we can see our function's going downward, and that's where we're seeing negative infinity come through. As x approaches negative infinity, so as we go off to the left-hand side, our function's getting bigger and bigger, so we're going off to positive infinity there. So with that, we can see our two scenarios visually with our graph and the idea of long-run behavior with a cubic function. Let's look at this one here. So evaluating the limit as x approaches positive infinity for 2x to the fourth, and the limit as x approaches negative infinity for 2x to the fourth. So if we just plug in 2 times infinity to the fourth power, infinity is just going to absorb all of that, so we're just going to be left with positive infinity. We do the same thing, but with negative infinity. Well, anything negative to the fourth power is going to be positive. So this is like a 2 times a positive infinity. So this is also going to land at positive infinity. So 2 times x to the 4th power, if we have an even power, it looks like a parabola. It's a little flatter since it's to the 4th power rather than squared. And because 2 is positive, it would be opening upward. So we can see that going off to infinity on the left-hand side and going off to positive infinity on the right-hand side. So that long-run behavior is coming through in that calculation as well. Let's take a look at some rational functions. Okay, so 3x minus 1 to 2x plus 5. If I plugged in infinity at this point, it'd be like having infinity over infinity, and that hurts the brain a little bit. That is not equal to 1, because there can be different levels of infinite, and you can always push it further, and this is where it's not strictly algebraic. So that is not equal to 1. We don't want to say that at all. So seeing infinity over infinity, I want to be careful. So I'll bring this back to the pre-calculus concept, but for a moment, what we're going to do is get a little tricky with our, not tricky, but we're going to use a trick to help us algebraically. So what I'm going to do is we're evaluating this limit as x approaches plus or minus infinity of this 3x minus 1 over 2x plus 5. What I'm going to do is I basically want to create fractions in the denominator. What I'm going to do is look at the denominator, and I see I have x raised to a power of 1. What I'm going to do, and this will make sense in a moment, and then we'll get lots of practice. I'm going to divide everything by that largest power of x, which in this case is just a power of 1. But we can only do that if we do the same thing to the numerator. So what I'm doing here is looking at the limit as x approaches plus or minus infinity of 3x divided by x is just 3, minus 1 over x, and then divided by 2x divided by x is just 2, plus 5 over x. Now I'm going to talk about plugging in infinity, and let's look at the positive one first. If I go limit as x approaches positive infinity of 3 minus 1 over x, 2 plus 5 over x, which is going to come down to evaluating 3 minus 1 over infinity, 2 plus 5 over infinity. So these spots where we're dividing by infinity, think about dividing by a large number. No matter what the numerator is, if we're dividing by a large number, dividing by something by 100, 1,000, that thing is getting smaller and smaller and smaller overall. So as that denominator grows, the overall number becomes teeny tiny. So if you think about 1 over 1, so there's just a bunch of zeros, that's basically nothing. As a fraction, that's super close to 0. And that's how we're going to write these two values. We're going to say if infinity is coming through in that denominator there, that's going towards 0, and this is going towards 0 as well, as a whole. So really, what I have is a 3 minus 0 divided by 2 plus 0 for a 3/2. And if we do this with negative infinity, it's going to be exactly the same. It's like some of the signs change, but the sign doesn't matter with zeros. But let's go ahead for the sake of completion, getting all this in. So 3 minus 1 over negative infinity over 2 plus 5 over negative infinity. It doesn't matter because that's going to 0 and this is going to 0. So it's a 3 plus 0, which is still 3, divided 2 plus 0, which is, or 2 minus 0 technically, 2. So this has long-run behavior of 3/2. Now, as a refresher of what we did in pre-calculus, when we have rational functions, we do a comparison of the degrees of the numerator and denominator, which the degrees are coming from the exponents. So we compare the two values, And if we call n the degree of the numerator and d the degree of the denominator, this is a case where the degrees are the same. So the degree of the numerator is equal to the degree of the denominator. Both have powers of 1. And when we do that, the rule goes for our horizontal asymptote. If those degrees are the same, our horizontal asymptote, it's always going to be y equals. And then in this case, we use the leading coefficients of the numerator divided by denominator. So you take those numbers and divide them up. So what we have for this graph is a horizontal asymptote of 3/2, which describes our long-run behavior. So that's where those limits are coming through for our function. Another one. Okay, so with this one, we're going to use the same idea of I'm going to adjust this in a way that makes it easier to evaluate the limits. Because right now I would have infinity over infinity, and that doesn't get me anywhere. So what I'm going to do is, again, focusing on the denominator, and I'm looking at the largest power of x. That's what I want to divide by. So in the denominator, I want to divide by 1 over x cubed, and whatever I do in the denominator, I also have to do in the numerator. So that means I am evaluating the limit as x approaches plus or minus infinity of 3 over x plus 2 over x squared divided by 4 minus 5 over x squared plus 7 over x cubed. Basically, all of those spots where we're plugging in x in the denominator, if we're plugging in infinity in the denominator of anything, that turns into a 0. Turns into a 0, turns into a 0, turns into a 0. So in the numerator of this, as I'm evaluating the limit as x approaches plus or minus infinity, doesn't matter if it's positive or negative, in the numerator I have a 0 plus 0 divided by 4, which is just 0. So we're going to have the same limit for both of them because we're just getting a 0 out. So we could write them separately or as that limit to plus or minus infinity. Oh, and then connecting this to pre-calculus. So this is a case where the degree in the numerator is less than the denominator. And when that's the case, if we go looking for the horizontal asymptote, it's always y equals 0. So if the degree of the numerator is less than the denominator, it's y equals 0. So our function might look something, not exactly, but kind of like this, where we're approaching 0 in the long run on both sides of the function. Okay, there we go. Now, this case, just while we're talking about the pre-calculus, this is a case where the degree of the numerator is more than the denominator. And what this would do is create an oblique asymptote or a slanted asymptote. And with that, we could find the equation, but really our function's going off to positive or negative infinity here. And so we just need to see which one is which. So our pre-calculus methods aren't going to get us very far here with kind of confirming our answer. So with these, I'm going to go ahead and keep it separated. So how about just as we go to positive infinity, I'm going to do that same trick of using just focusing on the denominator rather. I see just a single x, so I want to divide by 1x. So when we do that, we're taking the limit as x approaches infinity of 3x plus 4 over 1 plus 2 over x. Now that 2 over x is going to go to a 0. And then here, when we plug in x equals infinity, that's going to go off to infinity. So it's like we have infinity plus 4, which doesn't really do anything. It's still infinity, dividing by 1. So really it's like infinity divided by 1, which is a positive infinity. So we're going to get a positive infinity for that side, and then the limit as x approaches negative infinity for this 3x plus 4 over 1 plus 2 over x. As we plug in infinity, that 2 over x still goes to 0, and that 3x is going to negative infinity. Negative infinity plus 4 is still negative infinity, and then dividing by a positive 1, that's all going to be a negative infinity. And with these, you can always graph this function here, and see that it works. In fact, now that I said that, let's check it out. So we have 3x squared plus 4x over x plus 2. And we're looking at long run behavior. So as we go off to the right, sorry, I think that looks weird. There is a gap there. It did look a little strange for a second. Okay, as we go off to the right, we're going up and up, which means we're going up to infinity. As we go to the left, we're going down and down, which means we're going towards negative infinity. So with these, what we have is evaluating the long run behavior of these functions without creating the graphs, or without using all those little rules of how to compare the degrees and things like that. We're just using limits. And then this little trick of multiplying the denominator and numerator can kind of get us there without using those pre-calculus rules that we had.